Alright guys, this is a sample advanced 2D kinematics problem. One that is essentially kind of the rally car problem when we first started doing this, but I'm just going to show you a sample right here. Here we have a person on a bike, and they are taking off a sweet jump. When you were younger, did you ever like make ramps out of stuff and make the most piddly jumps? That's essentially what this is. Let's see here. We've got, we can see that they jump from a height here of 1.5 meters, and they jump a total distance of 1.3 meters. So not very much, not impressive at all. But the question is, what does this velocity have to be in order to make that particular path happen? Now I've been using kind of velocity t for total or tangent, and we get to that a little bit later. You can use any letter you want here, honestly. You could just use v by itself. As a matter of fact, you know what? Let's do that for this particular problem. Let's just go ahead and just make that v. And let's start filling out what we know. Well, making my chart real quick here. Don't forget, by the way, that when we do this, that if I do the initial, this is actually, this right here is velocity initial x, this is velocity initial y. Well, technically, actually, let's go back. That is just velocity x, because it doesn't change, as that is velocity x, as that is 0 here on Earth, and that's negative g. No idea what that is at all. Okay, delta s is really just delta x in this column and delta y over here. So to that end, let's go ahead and fill out what we actually know. Well, we still know gravity. We know that it wanted to end at a horizontal displacement of 1.3 meters. So that means this right here is a positive 1.3 meters. And we also know that the displacement, even though it goes above, in total change is going to go down by 0.5 meters, which means we know this guy right here is negative 0.5 meters. This would be negative when this arrow goes down or it lands below where it started, and it'll be positive when it lands above where it started. Now, we don't know what the velocity in the x or the velocity in the y are, but if I kind of zoom in on that triangle over here of v, if I did want to find velocity in the x, I would use trig, and I would take this amount, this total, times the cosine of 27 degrees. So this would be v cosine of 27 degrees, and of course this would be v sine of 27 degrees. And that is actually all the information that we know in this particular problem. So what I'm going to do here is I'm going to start over on the x side, because there's only one possible equation to use. Delta x equals vx times delta t. I'm going to start plugging in. I know that delta x is a positive 1.3 meters. I know vx right here is the total v times the cosine of 27 degrees. And I don't know t, so I'm going to leave it. Now the reason why we regularly use vt instead of just v is you don't want to accidentally get these two right here confused. They are not the same thing. If we go back to the triangle over here, you'll see that the v that we are using with the v cosine is right here, and that's vx. They are not the same thing. So let's go back over here. What we now have is an equation with two unknowns. We don't know v, we don't know delta t. And we can go to the y column here to figure out another variable. Now if we could straight up just find one of those numbers by itself, great. This is not really an advanced problem. Plug it in and you're all set. But that's not exactly how it ends up, because we don't know still v here, and we don't know t, which means we have two unknowns, which means this is going to be a system of equations, or two equations with two unknowns. Now, the first equation was picked because there's only one possible equation in the x, because acceleration is 0. But for the y, since there is an acceleration, we have all of the options of kinematics. Since all kinematic equations are made out of 4 variables, we have to decide what to put in there. We know we need to put in the variables, so we have to put in this one. We have to put in that one, because we need the same 2 variables in there. And ideally, we don't want any more things that we don't know, so we should put in knowns. So you'll notice I've put 4 check marks up there, so we need the equation that has those 4. there will be problems in which you're not using the exact same equation, and that's just going to be based on, hey, I don't know this thing. So for example, right now, based on those things right there, we should use this equation right here because that is the one with those four. However, just to give you a taste of another problem, let's say instead of knowing that that this is going to land 0.5 meters below, let's say we knew that it was going to go to the top of its path and it was going to be 0 right there. In which case we wouldn't know this, we would know that, and the equation would be this one. Because that's the one with the two variables that we know, this one, sorry, the two variables that we want, and the two things that we know. Now that's not the case, so we're going to work our way backwards here, so we have the exact same setup as before. There we are. And come back over here and just finish the problem. So we'll plug in. Delta y is negative 0.5 meters. VIY is V times sine of 27. Don't forget V and VIY are not the same. Delta t we don't know. Plus 1/2 times negative g times delta t squared. Now I have two equations with the exact same two unknowns, and therefore this is now a system of equations problem. This is where physics is done and technically math takes over, and of course we want you to know how to do the math, but just you should have this clear distinction. Okay, I can do this part, where do I need to focus on? Now the way I'm going to do this math is I'm going to come over here to this left equation, right over here, and solve for v, because as I see on the right equation, there's only one v, and the t is squared, which it's kind of wonky. You can certainly do that math if you want. But I'm going to divide by this and this, so I end up with v equals 1.3 meters over cosine of 27 times delta t. And then I'll substitute it in here. Negative 0.5 meters, oops, equals v is 1.3 meters over cosine of 27 times time. Okay, that was just this right here, so I now have the sine 27 times time. And running out of room a little bit, I'm going to combine those last two terms into just, or the first two terms there, to g over 2, negative g over 2 times delta t squared. Now I have an equation with just one value, so I just need to do algebra. You'll notice in this kind of middle term, these two t's cancel because there's one on top and one on bottom. And if you'd like, you can also see that sine is divided on top of cosine, which does in fact make tangent, if you prefer. There's a couple ways you could do this, just moving them around, simple stuff. I'm going to go ahead and add this over on that side and add that over there, which ends up as 1.3 meters, tangent of 27 degrees, plus 0.5 meters is equal to g over 2, oops, just did a tangent there, times delta t squared. Okay, and then multiply by 2 over g. Now when you do that, remember you have to multiply everything by 2 over g. So I'm going to put parentheses around that. 2 over g. I'm just going to use my whiteboard here to make this a little bit easier. Square root both sides. And there you go. Now, you might say, Spano, well, that's not what we were trying to find, which is 100% your prerogative. If you wanted to go find v immediately, you would have, of course, up here had to solve for t, and then plug it in twice and square it over on the right side, and that certainly works, and you should end up with the right answer if you do that. But that's not... I forgot to calculate. That's not what we're doing in this case because we found the algebra to be simpler. So 1.3 tangent of 27 plus 0.5 and then times 2 divided by g and square root the whole thing, and we get that the total elapsed time is 0.49 seconds, which makes sense. It wasn't that impressive of a jump. Now that's not what we're looking for, that is the total hang time, but easy solution here, system of equations. If you find x, just go ahead and plug x in to get y, or if you find t, plug t in to get v. So we have 1.3 meters, I just made that arrow right my way. over cosine of 27 degrees times 0.49 seconds is v. So v should be 1.3 divided by cosine of 27 divided by 0.49. And you end up with 2.9956, wow, 3.00 meters per second. I swear it just chose these numbers at random. That's hilarious. There you go. That's how you do one of these problems. The main difference, as we've already mentioned, I'll say it again, in any of the problems is really just, excuse me, how you choose that second equation, depending on what you're given up here. And now I will also add this kind of extra bit here. There are problems, for example, that have like the golf problem on our homework. It'll say something like, the path of the ball covers 302 meters on a good drive, okay? And then asks how high the ball actually went. Now, here's the problem. Some people will plug in delta x as 302 meters, which goes right here. But then velocity final in the y, they'll plug in as 0, which goes right here. Now this one is nice because it goes perfectly with what we said before. We're trying to look for max height. You're trying to find that delta y. Point being, you can't mix and match these. What you would have to do in this case, ignore this, go say delta y is 0 meters, use that to find whatever the heck velocity actually is, and then after doing that, do a whole nother set of variables to go find y. And there you go. That's how you do one of those problems.